Now the problem we have is because extreme weather events have local or regional impacts. People think they have global impact. I don't think that's quite true. The increase in frequency of these events is incorrectly used to support anthropogenic global warming. I think this is also wrong. Real global climate change have sufficiently large temperature difference. The best example I could think of are interglacial glacial cycles, where the temperature difference can be as much as 10 degrees Celsius. So most of the smaller changes, they're not really global climate change. It's just noise, if you ask me. Smaller differences can be seen in things like Little Ice Age, medieval warm period, and so on. Sorry, getting used to this. I think you've seen this slide before. The point about this slide is climate variability, additional monsoons in different parts of the world may be controlled by all these things. And a volcanic eruption in some parts of the world may change the balance of these oscillations. I won't have time to go through them, but I'll give you examples of different eruptions later onwards and how they may contribute to local and regional changes. Volcanic eruption clouds entering the stratosphere interferes with the jet stream. This is well known, depending on the eruption. And one of the things that volcanoes transported into the stratosphere in large volume is water vapor, as well as gases like sulfur dioxide and so on. And often this creates atmospheric rivers, causing major distribution of water vapor. And heavy rain may result in different locations. My classification of volcanic eruptions, I have reworded it a little bit. Basically, you have two main types of eruptions, subaerial and submarine eruptions. And then the third type are the mixed one. Subaerial eruptions has a tendency to warm the atmosphere initially, followed by major cooling because of obstruction of solar radiation arriving on the Earth's surface, and may cause all these different impacts that I've described. Submarine volcanic activity has the opposite effect. It has the potential of warming the ocean. So we have both cooling and warming because of these two main types of eruption, causing temperature either to go up or down. And this is very important. Ocean warming may cause a totally different effect, opposite of subaerial eruptions. But initially, an oceanic eruption forms a new island, and the new island becomes a volcano above sea level, and you may have subaerial eruption forming an eruption cloud that drifts around the world, so causing cooling. My model of subaerial volcano is shown in this slide. Now this example is actually El Chichong in 1982, and this was the first volcanic eruption cloud tracked by satellites going around the globe in 21 days. So, and this is particularly interesting for me in Hong Kong because it turned out to be the second wettest year on record. Because of the latitude, it's similar to Hong Kong. Subaerial eruptions discharge ash and aerosols. It warms the air initially, followed by cooling because of these ash and aerosols. There are many gases. Volcanic eruptions are great for forming clouds, and cloud distribution is a major problem because it changes the climate, at least regionally. For measuring subaerial volcanic eruptions, we do have a scale, what is called the VEI, the Volcanic Explosivity Index, ranking from 0 all the way to 8. The Yellowstone eruption is thought to be of a scale of 8. The biggest eruption in the last 150 years is Pinatubo, has a scale of 6. Usually, if we have a VI 3 or even 2 eruption, we can start to see weather impacts, at least locally and regionally. For measuring the spread of the eruption cloud, we have this A-train from NASA. We have different sensors. We can measure the height of the cloud, the aerosols and ash as it passes around the globe. So based on the location of the volcanoes, we can see how the cloud is being dispersed. Well, we start looking at extreme weather events. My examples of extreme rainfall years in Hong Kong is shown on this slide. We have a record from 1884 to the present, and I have given 4 examples. In 1963, our driest year on record in 1963 was due to Agong, the volcano on Bali. In 1982, when the Mexican volcano erupted, El Chichon, it turned out to be the 2nd wettest year on record. And in 1991, when Pinatubo erupted in the Philippines, it turned out to be the 11th driest year on record. But why only 11th? The eruption was in middle of June. Already 5.5 months have passed, so it's still a very dry year. Another wet year was 2008. The Chilean volcano Chaitan erupted. That's the one that closed some of the airports in Australia, Adelaide and Melbourne, as it circled the globe the first time. But 1.5 times after it circled the globe, it arrived in Hong Kong. We have the worst rainstorm on record. On one island, Lantau Island, we have 2,400 landslides. A single rainstorm triggering 2,400 landslides. So this is how I got interested in extreme weather events, because of volcanic eruption. So you have examples of very wet years and very dry years. But how do you explain such a change? Hong Kong is located at the margin of the biggest continent in the world, Asia. So wind shift. If the wind is coming from South China Sea, it brings moisture. If it's offshore wind, then you have major dry conditions, drought. So basically circulation change, so the northeast monsoon strengthens during drought years. We can come back to this and look at more details later onwards. The 1982 El Chichon eruption in Mexico is shown on this slide. For the first time, we have satellite tracking of the eruption cloud as it spread across the Pacific Ocean from the East Pacific to the West Pacific. It took 11 days to arrive above the skies in Hong Kong, and 21 days to circle the globe. So you can see in the last map, it circled the globe. This eruption is particularly interesting because of the large quantity of sulfur dioxide, which has major impact on the E folding time and then the rainfall. So this turned out to be the second wettest year on record since 1884. And if you can read all the details, so these are all the things which is normal about this year. The rainfall during the year at the Hong Kong Observatory's headquarters station is shown here. So the monthly distribution of rainfall. The eruption was in late March to early April. The annual rainfall in Hong Kong is shown here, and you can see the comparison to the annual rainfall. So it's the second wettest year on record. The normal for April is shown here, and then the normal for May. One reason why we say there must be a connection with the El Chichong eruption cloud is because of the timing of the heavy rain when it started. And then 35 days after the eruption first circled the globe 1.5 times, it came back to southern China. Guangdong has one of the most severe floods, killing 400 people. I think just now I mentioned the comparison. The missing flight, Malaysian airline flight MH370, about 280 people died. The vast sum of money spent on investigating the location of this missing aircraft compared to the loss of life during this eruption 35 days after El Chichong erupted. I think this is all driven by politics. And the money we spent, we still are inconclusive of the evidence. Just like carbon dioxide, how much money we are spending on it. But really, should the money be spent on preventing floods in different parts of the world? I think this is the irony of it all. Okay. The opposite of very wet years or flood years are droughts. And this is an example from 1991 Pinatubo. Now you can see the blue cloud, which is the eruption cloud at the beginning of the eruption. Already you have an enormous cloud system shown by the white color. So this is just water vapor from a typhoon passing Luzon at the time. So there's already vast quantities of water vapor in the troposphere. And then the volcano erupted, and it went up 55 kilometers above sea level. So it's a much bigger eruption cloud compared to the typhoon cloud, which only goes up to about 12 kilometers. And this is why we have a global drought year in 1991. Based on the study of Pinatubo by other workers, they have identified this E-folding time of 35 days. And I am now using this E-folding time of different volcanic eruptions to try to identify extreme rainfall in different parts of the world. It certainly works for El Chichong, which I've talked about because of the Guangdong floods killing 400 people. But we are also able to track other events based on satellites. In the oceans, we have the Argo network to measure ocean temperatures. So opposite to subaerial eruptions, we can measure ocean warming due to submarine volcanic eruptions. My model is indicated here. Different examples of submarine volcanic eruptions are listed here. El Hierro, which is in Canary Island. This submarine volcano erupted for 6 months in 2011 to 2012. and has major impact in the North Atlantic Ocean. Hunger is an earlier eruption, and we have also studied this. In fact, it has created hot water blobs at least 3 times that we have studied. Then in the North Pacific Ocean, south of Tokyo, we have Nishinoshima, a volcano 970 kilometers south of Tokyo. This submarine volcano erupted for 2.5 years, creating the North Pacific blob. And the impacts are listed here. So a whole range of impacts, including polar sea ice changes, have been identified. So quite a variety of things has happened because of this ocean warming. You probably cannot read that so well, but this PowerPoint will be available, I hope, for you to look at. What I've done is I've selected different oceanic eruptions and have identified the climatic impacts of them. So if you go through the list, I think some of these I will give more examples of in detail following this slide. In the Caribbean Sea, on the island of Montserrat, the Soufrière Hills eruption occurred on 11th of February, 2010. So you can see the location of the volcano here. At the time of the eruption, there was a cold front shown by this string of clouds. The North Atlantic Ocean was very cold, so this is the warm sector. The eruption happens to be in the warm sector of this frontal system. Now we can track the eruption cloud day by day. And this is one of the images that I can find. So this is the front, the cold front. And you can see the eruption cloud with the ash and aerosols. And this frontal system is heading towards Western Europe. So we can track it day by day. And what's interesting is, I try to summarize this rather than to show you a lot of these slides. The frontal activity storms was created, causing disastrous extreme rainfall. The eruption started on the 11th, and roughly about 10 days afterwards, the frontal activity storm arrived in Madeira, the Portuguese island. And the death toll of the floods resulted in 48 deaths. And another 8 days afterwards, Cyclone Cynthia, so the same storm system, has migrated into Western Europe, causing severe flooding along the coast. Again, major death tolls, 62, with wind strength of 240 kilometers per hour and 3 billion euros damage. Other countries affected, Spain, Belgium, Germany, and so on. So both storms, conclusively, we can show by this tracking, day-by-day tracking, were exacerbated by the Soufrière Hills eruption on the 11th of February. Right? So this is the sort of thing that we can do if we have these satellite images. Also the same year, we have the Iceland eruption, the one that most people cannot pronounce. I can't pronounce it, so I just call it E15. 15 letters after E. It erupted on the 14th of April, and this is the eruption that caused the transatlantic flight to stop for a couple of weeks. You can see the brown color, brownish red color, which is the eruption cloud. This eruption had major impact on both extreme rainfall and weather. This is a satellite analysis on the 20 9th of April, so about 2 weeks afterwards, Iceland is shown here. You can see a series of occluded frontal system rising into the stratosphere, and then the cloud system associated with the frontal system, bringing heavy rain. Slovakia had rainfall breaking records since 1818. So you can see temperature is in the red, and blue is the rainfall. And this sharp rise in rainfall in 2010 was the wettest year since 1818 by far. And you have serious flooding in Central Europe from Poland, Czech Republic, southern Germany, even Austria, and so on. Major transfer of water vapor deep into the continental interiors, into Central Europe, and even to Russia. Further down the road, it leads to severe flooding in Pakistan also. So during that year, 2010. In December that year, I was attending a conference on extreme weather event at the University of Cambridge in middle of December. When the conference finished, heavy snow blizzard starts to fall. I have trouble going back to Hong Kong because Heathrow was shut. Because of the blizzards, Heathrow doesn't have any ice moving equipment, unlike Gatwick. So they closed the airport, and I have to wait until Boxing Day before I got a flight back to Hong Kong. The cold weather that winter was partly because of aerosols and ash circulating the globe at that latitude, causing very cold winter that year with heavy snow in northwestern Europe. Extreme weather caused by El Hierro, this submarine volcano that erupted in the Canary Islands, Hurricane Sandy, the one causing death toll in New York, and the wettest summer in 150 years in the United Kingdom with serious flooding, shown by this blue, deep blue color, is shown here. So it's all because of the warm North Atlantic Ocean due to the heating up of the ocean regionally. So these are just two of the most noteworthy events that particular year. The long and strong 2014-2016 ENSO and associated weather changes are also very important. But this is a lot more complicated because multiple eruptions are involved. It also demonstrates the fact that every ENSO event is different. Normally, ENSO events, you have this warm water appearing off the coast of Peru around December. But this one is in August. So why is there such a big major difference? So we have to look at the factors involved in this particular case. If we look at all the submarine eruptions that occurred in the Pacific Ocean during 2012 to 2016, I've compiled a list here. So you have multiple eruptions at different locations, and they all contribute to regional warming in different parts of the oceans. Okay. But the most important contributor is Nishinoshima, the submarine volcano, which becomes subaerial after a new island was created, 970 kilometers south of Tokyo. So it erupted from March 2013 to August 2015, so almost 2.5 years. And this created what is called the North Pacific Blob, a region of abnormally warm seawater, up to more than 5 degrees warmer than normal, changing the pressure conditions of the oceans. So it was high pressure over much of the time, and then the weather associated with this large region of North America and the Northwest Pacific, so which you can see here. I think before we look at the map, I think we have to look at the sequence of events of the North Pacific blob. So we can identify these individual events from looking at these NOAA sea surface temperature charts. So they were all freely available to anyone interested. So what I've done is to draw up this information from looking at these charts. What has happened to the North Pacific blob? It first started off having a major patch of warm sea water all in one place. Then it gradually evolved because of ocean circulation change. It's spreading into 3 patches off the coast of Alaska, the coast of Seattle, British Columbia, and then off the coast of Southern California. You can see that it's quite different from the normal location of El Enso, which is off the coast of South America, off Peru. So in terms of weather influence, pressure change is very important. So you have high pressure immediately above the blob. The North American area has the opposite effect. You have a polar vortex developing. The cold air of the Arctic was sucked much further south over the North American continent, causing much colder conditions over the continental part of North America. And the opposite effect is that off the Pacific coast, you have 2 years without winters, National Geographic has published this. They say heat wave taking place off this Pacific coast is a sign of future global warming. But in fact, the biodiversity change is just because of the hot sea water and the migration of those marine life, especially if they can swim, and those which are benthic, they cannot escape, so they just die as a result, including otters and crabs and so on. So the sea surface temperature anomalies on the 29th of June in 2015, towards the later part of the North Pacific blob, the final straw in warming the ocean at the right location of ENSO was because of the Galapagos volcano, Wolf, erupted. So this is a VEI-4 eruption, causing the hot water to spread out in the normal location of ENSO. The Hunga Tonga eruption also occurred. This is a much earlier eruption that developed into a South Pacific blob. We have studied Hunga Tonga over the past 15 years, and for 3 different periods, it has created a South Pacific blob. This is not the biggest, but you can see an island was created and it became subaerial. So initially it was a submarine eruption, changing into a subaerial eruption. So the timing of the change may be important in terms of warming the ocean when it was submarine, and then cooling of the atmosphere when it was subaerial, and so on. And the dimensions of the South Pacific blob resulting from the submarine eruption may be of interest to us in terms of the ocean warming. The Wolf volcano is entirely subaerial. The eruption created lava flows entering the Pacific. Hot lava is 1,200 degrees Celsius, so it warms up the surface water of the ocean. So this at night time, you can see the hot lava pouring into the Pacific. So this may be the final straw in terms of the development of the ENSO event, heating up the seawater. So the situation after the Wolf eruption in August, end of August 2015. So the ENSO gives you a pattern of seawater distribution like this. Still 3 major patches of hot seawater. And it's not the same as previous ENSO. This is August, not December. So we need to explain the regional weather changes resulting from all these eruptions. Now, I talked about El Hierro in 2011, and then the North Pacific Blob, affecting the North Pacific Ocean to be quite hot. If we look at the Arctic sea ice, we can actually see the impact. So if you look at these different maps taken over different periods of time, we can identify sea ice retreat. In 2012, it was the lowest of this period. But the sea ice retreat is much faster in the North Atlantic in comparison to the North Pacific, which is the Bering Strait. The retreat, because Bering Strait is much more narrow, and the hot seawater is mainly from the North Pacific Ocean, so ice retreat is much faster near the Bering Strait. And we can see this in the map. So this is consistent with what has been found in terms of Arctic sea ice retreat by the distance from the hot seawater generated by ocean warming. So this is a simplified diagram, 2 ways to measure the Arctic sea ice. The drastic decline during 2012 is shown in the first drop, while the North Pacific Blob is the explanation for this less sharp decline in Arctic sea ice. So it's consistent with the observation records. We look at another South Pacific Blob which occurred in 2019 to now 2020. This is the biggest. Marine heat wave east of New Zealand, high pressure, and the total area is as much as 1 million square kilometers. The size of Texas has been reported. The temperature difference is 6 degrees Celsius above normal, so much hotter than compared to the recent Hunger eruption. Total thickness of the hot seawater is 50 meters. A New Zealand professor, Renwick, so that's his conclusion, heated by the sun through natural causes instead of global warming. So this is the South Pacific Blob developed at the time in 2019. It's the biggest out of the 3 that have investigated. Impact on Antarctic sea ice is shown here. During this very short time period, major sea ice retreat can be seen. So this is over this short time period. So these are both images from the satellites. Major calving of the sea ice and record temperatures at Eagle Island Station was reported. Well, coming to the last Pacific Blob, why is it much smaller? You remember this eruption initially was submarine, but it was not long lasting. It only heated up the seawater temperatures to about 2 to 3 degrees Celsius above normal. But then it created a new island, which erupted subaerially, 58 kilometers above sea level. So cooling started to take place. The convection transfer of water vapor was enormous because it's an island volcano. So all these processes we can identify. So interference with the jet stream, the rising plume caused the jet stream to meander, and this generated atmospheric rivers. Record rainfall in both New Zealand and Eastern Australia was found. So the major transfer of water vapor, and water vapor is of course the most important greenhouse gas we know of. The 35 days E-folding time of this eruption cloud resulted in heavy rainfall somewhere in Indonesia. So after circling the globe about 1.5 times also. The extent of the hot seawater during this submarine eruption, you can see, is much less important in terms of area coverage. So these are fortnightly maps of the coast, of the east coast of Australia, around New Zealand and so on. So the hot seawater developed is not so high in temperature, only 3 degrees Celsius above normal. The heavy rain has an impact on cooling the seawater. So this is why the blob is not as well developed. So on the 15th of January, you have this major subaerial eruption, transferring vast quantities of water vapor into the stratosphere. And this water vapor hang around for at least a year or more, resulting in southern hemisphere to have much more rainfall than normal. So the South Pacific blob during January to February can be seen here. So the environmental factors influencing weather during this eruption can be summarized here. We have published this in Saltbush Club, I think, together with my former student, Alvin Wong. So we've identified all these different events as being a factor. Usually after a volcanic eruption, whether they're submarine or subaerial, the first month is the critical time to look at changes. If you look at things about a year afterwards, it's not so clear. It's better to track it day by day in order to nail it down. Another example of extreme rainfall impact, I think sea level, which we talked about the last year when I was here. Hong Kong's tide gauges are shown here. Victoria Harbour is where we have the longest record. And I can show you even the tide gauges shows a record influenced by extreme weather events. If we look at the tide gauge record of Victoria Harbour, which is from 1954 to the present, so this is the annual mean sea level plot. It's not a straightforward rise in sea level. What we are lucky with, the record we have included both the driest year in 1963 and the wettest year in 1997, since our record began in 1884. So what is worthwhile doing is to look at these 2 years and see what really happened. 1963, you remember, Agong erupted on Bali. You see a drop in sea level to a more or less a minimum. How do you explain that? Less rainfall means high pressure. Less runoff from the River Pearl, which influenced the sea level at the mouth of the River Pearl. Well, 1997 was the wettest year, so what caused wettest year? Heavy rainfall. Heavy rainfall means low pressure. And you can see accelerated sea level rise around this period from 1990 to about 1999. 1997 is near almost the top of this peak. So both these are better explained by extreme rainfall and surface runoff from the Pearl. So extreme weather events influencing sea level. And if you think sea level is all indicated by tide gauge to show global warming, why is this influenced by individual dry years and wet years? In summary, some of my main conclusions are shown here. Maybe I should leave it open to questions. I think extreme weather events are very interesting for us to look at. And my pet subject now, because I have much less time and I'm not as good as I am when I was younger, is to look at 35 days after a major eruption, where the eruption cloud has gone to, and look at extreme rainfall in these locations. So this is my pet subject now.